I'm in Aberdeen in November, and I'm quite happy to be warmer than I was outside. So this is great. It turns out my Campbell roots have completely abandoned me, born and raised in California. If it's anywhere distant from about 23, below, above, I'm completely gone. So this is a thrill, genuinely, to come up. I just happened to be in London this week, and 3 separate universities found out and invited me to come visit. And so you're, along with UCL and University of Birmingham, it's actually my first trip in England outside of London to go visit them. It's an interesting thing. In California, you cannot hop on a train and be somewhere else in an hour. It's just, it doesn't work that way. It's 6 hours just to get to Los Angeles from San Francisco, and that's our neighbor. So it's great to be here. I am reminded that my talk topic is the neuroscience of trust, but I'm going to be honest, partially because there are some younger attendees that might have their own questions. What I'm going to do is start with an introduction to my work, which is the coolest job in the whole world, and it's quite broad. And so my work ranges from artificial intelligence to neuroscience to economics and entrepreneurship, and I'm genuinely happy to chat about anything that anyone might want to. But first, I'll take a sip of tea, and then say that my professional career began as a theoretical neuroscientist. So I did my PhDs at Carnegie Mellon. A very nice Scotsman left some money behind after he died, and actually the Mellon banking family hated him. They would be so aghast to learn that a university is named after the two of them conjoined. But I did my PhD in computational neuroscience and psychology there, and then had a joint appointment at Stanford and Berkeley, in particular at a place called the Redwood Center for Theoretical Neuroscience. And if you've never heard of theoretical neuroscience, there's a couple of easy ways I can describe it. One is you can just substitute the word lazy for theoretical. That's what all empirical neuroscientists think of us. They actually do really hard research with things like rabies retrovirus tracing and macaques and the neurophysiology. And basically, they got to stick wires into cats or do really interesting things, put genetically engineered green fluorescent protein into the brains of clonal mice and see how different parts of their brains activate. We just make fake brains on computers and teach them how to do things. And I don't know if I should be proud or if I should apologize, but almost all of the really cool AI stuff you are surely aware of today pretty much comes out of my field of research. One of the most notorious individuals, Jeff Hinton, who effectively developed the deep neural network, although I will say everybody was working on a similar concept at the same time, but boy, he got an amazing breakthrough. He was at the University of Toronto, and his students and my lab were really good friends, and whenever we met up, we'd share information. We, unfortunately, didn't come up with that breakthrough, so he's rich and famous, and we all have to still be scientists. But I was at Cal and Berkeley, Stanford and Berkeley, and my wife, who was a professor of education at Berkeley at the time, this is a reference that is only going to work for some of you. She got some of her education in my neuroscience. I got some of my neuroscience in her. It's a Reese's thing. See, you're all too young to get a bad old candy ad joke, but we mashed up some of the machine learning I was working on, some of my neuroscience research, with her education research. And we thought, is this an experiment? Or maybe it's a company, a startup. And so I made the terrible decision of starting an AI-driven educational technology startup in 2008. I will tell you there were no real AI companies back then, and even education, if you have heard of Coursera, Khan Academy, none of that existed. Sal Khan was trying to start Khan Academy at the same time. I met him a few times. I like Khan Academy. I can't say the same about Sal Khan. But we went out and had the wonderful experience once of pitching some venture capitalists on this little street outside Sanford called Sand Hill Road, where all of these venture capitalists, people who put money into startups, have their offices. And I remember one of them in particular patting me on the head and telling me I had such a good idea, and then voting not to fund us. It turns out being a company started by a couple of weird women is not necessarily a great recipe for getting a bunch of Stanford frat brothers to fund your company. But we made it work anyways. And we ended up selling the company, and I got to admit, I got kind of addicted. I love being a scientist. I loved being at university. I still live in Berkeley. In fact, I walk onto the university all the time, and I'm now on several boards of different groups at Berkeley, including the new Neurotech Collider Hub, which sounds very cool, and will be someday once we really get it going. But there was something about building things that actually directly affected people's lives. As an undergrad, I got my start with artificial intelligence. Actually, maybe I'll start even a little further back. I have a bit of a colorful history, but I'm going to just skip all of it and say, read between the lines, I returned to university in 1999 and had this crazy idea. Despite never having been a particularly successful student before, everyone thought I was bright, but I was not a good student. There's a reason I was returning to university. But I figured I was going to do my whole undergraduate degree, maybe postgraduate here, in a single year. And so being very snobby, I figured, it's got to be a STEM degree, right? So I figured out which ones I could actually complete, given the various unit requirements and everything. And it was math, economics, and neuroscience. And I thought, math, what am I ever going to do with that? Little did I know. So I literally flipped a coin between neuroscience and economics. It came up heads, so I studied brains. Again, literally, that's the way it worked out. And sure enough, I did, the UC system was on quarters, so I did in 5 quarters, 7 classes a quarter, plus 2 research projects, and I got perfect grades in every single course. It was crazy. I genuinely had never had success like that in my life. But there were several things that were different, one of which is I sat up front in every class, keep in mind, not expecting to be so successful with the marks in my class. I sat up front and simply thought, how can I use this? What can I do with this information that they are giving me? And wow, it was transformative. My undergraduate honors thesis was based on $5 million worth of funding from the CIA to build a real-time facial analysis system to tell if people were lying to them. Something, obviously, that spies would be very interested in, but I thought, wow, I bet there's something else I could do with this. And so I later got to use what I learned on that project. My undergraduate honors thesis was it wouldn't be called deep nowadays, but it was a neural network that could tell, it would find your pupils and your philtrum. If you have not heard that, that's your little weird thing above your lip. Find it, orient your face, and then it could tell if you were truly smiling or faking it. It's in the supraorbital muscles around your eyes. A Duchenne or a non-Duchenne smile. And it was so cool. I built a machine that seemed like it was doing something so fundamentally human. Seeing a real smile. Now, 25 years later, I will say very clearly, it's one thing to be able to do what we were doing, which is detecting shifts in the muscular structure of the face, what's called facial action codes, and then identifying that there has been a change. So we could read expressions. That actually doesn't mean someone's happy or not. It doesn't mean someone's lying. It turns out all of that is a much more complicated story. It's more like accents. Everyone has different facial accents. We don't think about it much because we didn't have to learn how to read faces. But if anyone here, we have enough people, maybe someone is on the autism spectrum, you do have to learn to read faces. So years later, I took what I learned from funding from the CIA and I built a system for Google Glass, if people remember this, a thoroughly mediocre augmented reality system that Sergey Brin at Google built as a pet project. And they gave me an early release pair. And we came up with a system that could read facial expressions and tell whether you're smiling or frowning, and then would write it on the screen. And you could imagine, I guess you could try to build a lie detection system. So you walk around like a cyborg, or I could, trust me, I've had many banks ask me this, could you like float the credit scores over the head of everybody in the room? Pull up everyone's social networks. There's a company that's doing that. Sell that information to the police. You could do all these sorts of things, none of which I'm interested in. We built it for autistic kids so that they could learn how to read facial expressions in natural interactions with other people. And it works. And it works so much better than what amounts to the current standard, which is cartoon faces on flashcards. And then later, actually, reverse that, earlier, I actually got to use the same technology to reunite orphan refugees with extended family members in a UN project called Refugees United. So I got hooked. What you could do with these technologies. I'm still fundamentally a neuroscientist. AI is a tool, really powerful one. And all of my other talks on this trip have been about AI, so I'm going to try not to just sit on this topic, but again, please, as you see, there's no slides. I much prefer to just talk to the audience, and if anyone has a question or wants to go deeper on something, just stop me. Trust me. I will be able to come up with something to say. In about 5 hours, you will all be weeping and begging to be released. So I got hooked on this idea, and in grad school, I built one of the first what are called convolutional networks. So it's a network that kind of slides over the information in time, and we used it to hear. So I literally walked around the parks of Pittsburgh, Pennsylvania with a microphone and a laptop in my backpack and recorded sounds. And as I was recording them, my neural network learned how to hear. And what it learned turns out to be almost identical to what our mammalian ears do. So I got to write some fancy papers about that, which was really cool, and made the computational neuroscience side of my education very happy. And the psychology department said, you know, clearly you have a very nice paper and it got published in Nature and everything, but it's not really psychology, is it? Like, please just run an experiment so we can pretend like you're a psychologist. And so we came up with this idea of taking our system. It learns how to hear. Well, there's another domain in which human beings have to learn to hear. Well, a couple of them, obviously when you get born. There's a degree to which you're learning how to hear. And in grad school, I wrote a whole review paper about the ascending and descending subcortical auditory network. So lots of fun, I'm sure, to the 2 people in the whole world that have ever read it, which, by the way, doesn't include me, because, but there's this other group, which is people that have a cochlear implant surgically installed later in life. Obviously, if you have it installed early in life, you also have to learn how to hear, but that's a cool thing. If you don't know what a cochlear implant is, it's basically a hearing aid except it literally gets wired into your brain, into the 8th cranial nerve, the auditory nerve. And it restores hearing to people that are profoundly deaf, which, to be fair, can be very controversial in the deaf community. But if you do this in a little baby, it can be really hard to tell they were ever deaf. By the time they grow up, you do it at my age or later, when your brain is not, it's kind of settling in and it doesn't think it has to get up off the sofa so often anymore. It's really hard. And, you know, people that love music and have a cochlear implant put in often stop listening to it because it can sound so unpleasant. And sometimes people get it. You often just do it on one side because just in case, because you have to go completely deaf on the side they put the implant in. And they'll go through the whole surgery and experience all the recovery and the challenges, and then after a little while just turn it off, because who wants to heal the world? If you want a sense of what it sounds like, imagine someone had tuned a bunch of garbage disposals for slightly different frequencies, and they were just turning them on and off as sort of like a parody of human voice. And that's kind of genuinely what it sounds like if you get this put in later in life. And we thought, well, what if we built in a machine learning system, artificial intelligence, and it can do some of the learning for them. And sure enough, when we actually ran experiments, people could hear much more of speech and noise than they could ever have heard before, like almost immediately. It was so exciting. I got to build the first cyborg, the first system that had a machine learning and a human learning component literally wired together. Which, by the way, is what I told people when I was interviewing for grad school. After racing through my 1 year and having very little at that point to show other than a completely unjustified scholastic record, is they'd say, so what do you want to study? I actually remember I was sitting next to someone. It was at Northwestern University in Chicago. And I said, what do you want to study? And they said, well, there's this protein cascade in yeast. I'm like, what? I thought this was a neuroscience department. It's worth knowing that to a molecular neuroscientist, we're all approximately yeast. Like, for them, there's no big difference between us and yeast. Just like we're spherical cows for physicists. And then they asked me what I wanted to study. And I said, cyborgs. And they literally scooted away from me for fear my crazy would rub off and they wouldn't get in either. But it turns out in neuroscience, we call it neuroprosthetics. And it's this amazing field. In some real sense, we get to build better people, largely focused on challenges. So at not the last World Cup, but the one before it, the opening kick was from a man who was profoundly paralyzed. He's literally wearing an exoskeleton out of science fiction, and it was plugged into his motor cortex. And he imagined walking, and so he walked very slowly. This was not messy on his best career day. I don't know, I'd pull an Aberdeen reference here, but I cannot name many, forgive me, Premier League players, much less Scottish League players, so I'm not going to be able to do it on the fly. Though I did watch a heartbreaking loss by Aberdeen recently, so I just thought I'd brush up just for the visit. So this gives you a little sense of my background and why I got addicted to the idea of building things that help people. So after we sold my first edtech company, I started my second edtech company, and then I had a series of companies in what's called HR tech. You know, who decides who gets a job? Well, I wasn't very happy with how those decisions are being made. Maybe AI could help there. So we had one of the very first companies in the world in that space, and then another. And so now this year, I'm celebrating the launch of 3 new companies. They add up to my 12th at this point. There's the CEO, which genuinely I have learned over the years, hire actual adults. I should not be in charge of anything. But chief scientist is a great job. And if you can scam everybody into it, chairman of the board and chief scientist, so your own CEO works for you, is truly unconscionable from a business perspective, but it's a great job. You just get to do whatever you want. These three companies, so one's a nonprofit and two are neurotechnology. So after my little detours into education and human capital workforce, now I get to go back to where my original experiences were. Believe me, at some point we'll come back to the neuroscience of trust. So the first, we have taken this fascinating finding out of MIT. They discovered that if you can stimulate your frontal lobes, prefrontal in particular, and related areas, the hippocampus, entorhinal cortex, we think of where memories get stored long-term and held also short-term, so also dorsolateral prefrontal cortex. If right now you're tracing my words over time and you're remembering things, if I said, what is the last thing I just said? That's your dorsolateral prefrontal cortex coming online and desperately trying to remember and then realizing you weren't actually paying attention. And as we get older, these systems slow. They literally slow. So if we record the activity around your prefrontal cortex in all these different areas, then you'll see some really interesting things happen. When you're working hard on remembering something, you see this broad connectivity between here and all these areas towards the posterior, the back of your brain, and it runs at about 8 hertz, 8 times per second. These areas kind of beat in synchrony, called coupling. But also when you're thinking really hard, when you're speaking, when you're listening to someone, and you're thinking hard, you're doing a hard math problem, we see other areas light up, but also particularly in the prefrontal areas, we see what's called a gamma activity. So this is like 30 hertz, 40 hertz, so getting a lot faster, 40 times per second, and up even beyond that. And what's noticed is this kind of slows over time. What helps you hit those 30 hertz are what's known as inhibitory interneurons. So all these specialized cells in your brain, and their whole job, in a weird way, is to slow down the firing of the other cells to help synchronize them. Because if everyone in this room was talking, and talking completely on your own, it would be gibberish and noise. But if instead we all synchronized and said the same word at the same time, people all around the building could hear us. So the same principle's going on in your brain. If you can get these areas to synchronize, even though in a sense the total firing rate across the brain goes down, because they're synchronized, they can push the signals through better and cleaner. And that begins to break down. And I don't mean break down at my age. I mean by the time you're in your maybe mid-20s, depends on a lot of factors in your life, but sometime in your 20s, this stuff kind of peaks out and then it slowly and healthily declines over time. The great thing is all sorts of other things get better. But under certain conditions, probably the most famous is Alzheimer's, things get really disrupted, and that slowing of the synchrony and the disruption of these interneurons, that greatly accelerates. And all of these terrible symptoms, not remembering the names of your own family, it starts with where were the keys and ends with terrible stories of loss. And so at MIT, there was this finding that if we could go in and stimulate your frontal lobes at 40 hertz, artificially stimulate them, 40 hertz, alternating current stimulation, like we're flipping a switch on and off. At 40 hertz, it slows the progression of Alzheimer's. And so a former postdoc of mine ran into a student at University of Copenhagen, technically University of Copenhagen, and they had this great idea. We could build a light that flashes, strobes at 30 hertz. But I don't know how many here have taken a psychophysics class on the color perception, but there's this famous trick of light in which any color can be made out of a combination of 3 other colors. That's why we have these 3 pixels combined together, these 3 different colors of pixels. Red, green, and blue is not exactly accurate, but that's the terminology we often use. And any combination of red, green, and blue together can give you any other color. But you can also do the opposite. What if I just wanted this light to be on, but actually we're going to spin this color wheel and cause the 3 pixels to all change at 40 hertz, but change precisely in relationship to each other so that you can't see it? Does your brain still synchronize to that 40 hertz activity, even though it just seems like a light that's on? You could read a book by it. It turns out that it does. And it turns out in our, both originally our animal trials and in our human trials, it actually reduces both the biological and behavioral symptoms of Alzheimer's. And over this last summer, a truly terrible thing happened to me, but it's a thing which is kind of inevitable for all of us. My mother had an amazing long life at 83. The week before this terrible thing happened, she drove herself. She was still teaching school in California. She drove herself to school, not full time, but several times a week. She'd go in and work with kids, and then she had a stroke, a massive left side stroke, and she wasn't found for quite some time. And although she came to at the hospital, we spent the next month at her bedside. We managed to get her home, and so my mother passed away over the summer, which is sad, but she had a truly amazing life. But it ended hard. Like many people experiencing a stroke, she became aphasic, which means not only in her case could she not produce speech, but she couldn't understand it. So she could recognize us, she could understand her circumstances, but if you asked her to point at pictures, can you point at the lion for me? She just had no idea. It's actually hard to understand what the experience of aphasia is. There is an amusing video I saw once of a patient, a split brain patient. And this isn't aphasia, but it does give you a sense of how strange the brain can be. So in a split brain patient, there's a separation, usually surgical, to help prevent seizures in epilepsy. So it's split, and if you do it right, you can show information to one side of the brain and not the other. And as some of you may appreciate, the left side of your brain is tied, the left side of your cortex is tied to the right side. It's a little more complicated. It's tied to the right side, the outside of your eye, the lateral part of this eye, and the medial part of this eye. But this field of vision all goes to this side. Well, this is, for most people, the language side. For most right-handers, you're pretty strongly lateralized to your left side for language processing. So, well, this guy had a split, and so you could show him pictures of objects that, in a sense, he could recognize, but he couldn't produce the word for. So they'd show a clarinet over here, and say, "Can you name it?" And he's like, "It's this thing. It's this thing for music. It's I can't. I just." And in the video, it's really interesting because he's clearly playing a clarinet, but he can't produce the word. And then he looks down and sees what he's doing and says, "It's a clarinet." Our brains are so fascinating. My rule of thumb for the brain, which has never steered me wrong, is however complex you think it is, it's more complex than that. That doesn't mean we don't understand anything. We know a huge amount about the brain. And every time we learn a big new thing, we discover how much more we don't understand. This has all been detour. So my mom had this terrible experience. She was aphasic. And I thought, well, what if we could use our light focusing not only on 40 hertz, but the 8 hertz I mentioned earlier, at the same time, and speed up language recovery, even though I knew it wasn't going to help my mom. Maybe it would help somebody, and it works. So building the system for Alzheimer's, we're actually building a whole new version of that system, hopefully to help people recover from strokes and traumatic brain injury. And my big ambition, put it like directly on a tablet. You could read a book and treat neurodegeneration at the same time. So it's amazing. I have another company called Dionysus, and it started, strangely enough, coincidentally, also out of MIT, at a conference I was at. I'll skip the longer story, but it brings together a bunch of interests of mine. Epigenetics and artificial intelligence and the understanding of the neuroscience of depression. And what we found was kind of fascinating. I'm going to tell it a little bit in reverse. I had come up with some algorithms for natural language processing, artificial intelligence, and it listened to these young adult women talking in social media online. Originally, these algorithms were developed to identify suicide risk in teens on social media. But for reasons, we put it into the history of social media use, Twitter and Facebook and so forth, that have been volunteered to us by these women. And we looked at it. And keep in mind, what we were measuring, although we didn't use these words with them, was suicide risk. We just called it stress. And it's not a bad measure of stress. So we have this artificial intelligence that can listen to people talking online and give us a sense of how their stress levels are changing, fluctuating over time. And in these particular women, and in no one else we were looking at, the stress levels were going up and down and up and down, roughly every 28 days. We looked at lots of other women as well, but didn't see it. Only in these women. So what was different about them? So if you're a young guy and you're not quite following what I'm saying, their stress levels were tracking with their menstrual cycle, up and down. And that was really surprising. Not because every now and then a bad period doesn't make you a little stressed out, but that we weren't seeing it in anyone else. And it was so pronounced. It was like a sinusoid. Well, what was different about them was we had identified an epigenetic biomarker. So we all understand genetics. We have these genes get translated into proteins. It becomes, in some sense, who we are, but it's such a more complicated story because epigenetics is essentially a story about how certain aspects of our genes get turned on and off by development, by our environment. In fact, the darkening of skin with sun exposure is an epigenetic phenomenon. A lot of learning in our brain has an underlying epigenetic phenomenon. So these genes can get turned on and off in incredibly complex ways. Well, in these young women, they have particular genetic alleles that are turned on, and every one of them had been diagnosed with postpartum depression. And long before they'd ever become depressed, we could see in their language patterns essentially the pre-echo of that depression. Their mood states are yoked to their hormonal states. And as a result, when their hormones become particularly disrupted during pregnancy, which affects 15% of mothers, it is the most common complication of pregnancy around the world. And yet the public health system in the UK, the US, Canada, and Australia is officially, this is a really terrible thing, but it would be too expensive if we treated everyone. So we'll just wait, and if you get diagnosed, then we'll send you to group therapy. Well, we have now the first ever biological test, and it works before you're ever pregnant. It would be impossible without artificial intelligence. It would be impossible without our understanding of epigenetics and the ability to do assays cheaply and easily. And so today we are starting our first human trial with the NIH in Atlanta, Georgia. We're doing it in a maternal healthcare desert where they don't have an obstetrician. They don't have, this is the States. You get what you pay for there. So there's no national health, making certain that everyone gets at least a certain level of care. And so these women are going into health clinics to get checkups for themselves and their babies. And so we're running right now this trial, which includes the use of our artificial intelligence to be able to analyze their speech patterns, so which we can do for free. And the blood tests, nobody can do for free, but we can do it for very cheap, and we're giving it away for them. But the company exists also. So these are the kind of really cool things I get to do, and it isn't even my day job. Believe it or not, this is all preamble. You will no longer trust anyone with the title of the Neuroscience of Trust, but I promise we'll get to it. My day job is I run a philanthropic lab. People bring me challenging problems. Dr. Ming, my daughter has 500 seizures a day. Please save her life. Dr. Ming, my son can't enter REM sleep. It's like the closest thing to an episode of House I've ever come across. Plenty of people can't enter REM sleep. They die. But it turns out there's about 5 people at any given time in the world who can't enter REM sleep, and for some reason they don't die. It essentially means you can't really effectively fall asleep. You can't get the benefits of sleep. I've had this kid, he was alive. He lives in Cambridge, Massachusetts, right in between MIT and Harvard, but nobody could figure out what was going on. Trust me, no one calls me first. The person who calls himself a professional mad scientist online is no one's first call, but sometimes nobody else is able to help. And it's not just medical. Dr. Ming, we know our company has bias. It's in its promotion process. Can you help us develop an economic model so that we could show our board, yes, we promoted good people, but we missed the opportunity to promote even better people? Because, I won't name the company, but because we have a very long history of not promoting women at the same rate as men. Or from Kenya. Dr. Ming, we do everything the World Bank tells us to do. Our education scores on the international education standards go up every year, and still nobody hires our citizens. Please help us figure out what's going on. And if I think my team and I can make a meaningful difference, I pay for everything, and whatever we invent, we give away. It is the best job in the whole world. It's a very expensive job, turns out, but it is the best job because you just get to help people, and I still get to be a scientist, and I still get to be entrepreneurial. Every now and then, one of these things, we discover something that seems really interesting. It has legs. We can explore it further. But the best example, which I can't recall what I shared with the online talk, but I certainly have shared in previous talks down in Edinburgh and Glasgow, is when my son was diagnosed with type 1 diabetes, and I hacked all his medical equipment. Turns out I broke all sorts of US federal laws. And I, unbeknownst to me, developed the first ever AI for diabetes at the time. And again, the best part, as much as I loved geeking out about hacking that stuff, and wonderful, the many parents of diabetic kids that had gotten started on this. So I didn't have to figure out the engineering. I'm a scientist. I'm a computational scientist. But it turns out we are very different than engineers. A thing that the rest of the world I don't think fully appreciates. And we built this, and we helped our son at a 40% reduction in how often his blood glucose levels were high. If any of you aren't familiar, this is an autoimmune disease. Your own immune systems destroy the cells that make insulin. Without insulin, you can't get sugar transported from your blood into your cell. You can eat all you want and effectively starve to death. I have a whole long story about it, but I will simply share the punchline here is after we helped our son, I got on the phone with every major device maker in the world, and I told them exactly how to build it themselves. I also let them know that I told their competitors how to build it. Sort of Glengarry Glen Ross style. The first one to bring this to market gets an extra $1 billion on their market cap. The second one doesn't go out of business. Number 3 and all the rest of them are out. I do a good, mean Alec Baldwin impersonation, for those of you who know it. If you don't, go see it, or maybe wait a year or two and then go see it. It's foul. It's amazing, this idea that you can help people. Every time I make a terrible career decision, giving away this algorithm, for example, or I've had some really cool job offers over the year. Uber called me up looking for a chief scientist to help build their self-driving cars. I don't know how much you know about Uber and its original founder, Travis Kalanick, but my answer took about 3 seconds, and it was, hell no. He's a human train wreck. I got a really cool request from Netflix to be their director of algorithms. I love movies. I really love movies. But gosh, I didn't really want to be picking, the next thing for someone to binge on that night. That didn't excite me. And it was also the pitch. We have the gnarliest data problems. The pitch from Uber was, we're all going to get rich, which is never the right pitch. Not for me, but nor is we have gnarly data problems. And who's alive at the end? I actually believe movies can truly change people's lives. I have a philanthropic side project right now to actually measure how the media we consume when we're young actually causally changes long-term life outcomes. I'd love to be able to show. I grew up, if you want to know who I am, my Sunday night with my dad was first, the public television in the United States is essentially a bunch of things bought off the BBC. At least in the late 70s and early 80s. So it's a mix of some US and a lot of British television. So we watch Nature and Cosmos and all of these science shows. And then we'd go into Monty Python and give it a little while, Blackadder and all this stuff. And then Doctor Who. And I came up with the terrible realization recently that, the classic question kids ask each other, what superhero would you be? What superpower would you have? I realized, God, I wish I was smarter than I am and I could live forever so I could do more and more. And it would be really cool to travel around like in time and space. And God damn it, Doctor Who is my superhero. That is so unsexy. But that's every night, that's every Sunday, that's what we watch, and it kind of foundationally became who I am. And I say this somewhat pointedly, I didn't love the writing on the recent series of Doctor Who, but just the idea, if you'd had a woman doctor earlier, might that have changed some of the possibilities for a number of women, young women growing up and seeing a superhero that isn't an 80-year-old crank of a man. So I get to do all of this stuff. And it's wonderful. Best job offer, I got a cool one, which is running Google X, being second. So my job would be to take cool ideas and turn them into companies. I already like what I do. But the best offer was from Amazon. Amazon said, it was a cold call in about 2015 or 16. Dr. Ming, in 7 years, we will be a 1 million person company. They were wrong. They were 1 million long before then. But your job will be to make their life better. So someone actually pitched me. Not their idea of who I was, but what I actually cared about. And so I actually went up. I didn't have high hopes, but I went up to Seattle and I met with everyone there. Maybe unsurprisingly, Jeff Bezos' idea of a good life is distinctly different than mine. One of the things they would have wanted me to do is to make people happily choose to leave after about 2 or 3 years. They have a very different idea about humanity than I do. But I think they genuinely believe it. So I went up, I actually offered, if I can make 1 million people's lives better, I'll do it for free. Call me a fellow, and I will do everything I ever dreamed of solely for you. And they said, we'll get back to you about that. So it's been like 8 years. I'm still waiting for the call. I mean, it's an amazing place. And honestly, having all of arguably the largest private company in the world as my mad science lab, it was appealing. But I get to help people anyways. And that is amazing. And in fact, I just started this third company. It isn't a company, it's a nonprofit. It's called The Human Trust. And it's this new idea, inspired by things like the UK Biobank. It's a data trust. All of the data being generated by my new companies, they don't own it, which is very uncommon. The 16 of the largest neurotech companies in the world right now have state very clearly that they own all the data coming out of your body. And furthermore, 15 of the 16 reserve the right to sell it to anyone. So I thought I should put my money where my mouth is. And all of the data we generate is actually owned by the trust, and the trust's sole fiduciary responsibility, its sole responsibility, is to the people generating the data. Those moms struggling with depression, or the people with Alzheimer's, or anything else. And so I've actually donated all of my philanthropic work into the trust, and we're going to relaunch a whole bunch of things. All right, it's preamble done. Trust. I've got 5 minutes left, and we'll get into all of it. But it was born out of one of these moments because, as I alluded to, yeah, I mean, there is something special about being able to directly help a specific person. A mom from South Africa called me once and said, my daughter has a life-threatening egg allergy, and there's like egg proteins in everything. And it took me 5 minutes to find a lab that had just invented, essentially a thing you just wave over food, and it picks up on the egg proteins that are in it and alerts you to it. And I just connected them together. I did almost nothing, but it felt so good. But I try to balance those direct cases that just help a person with things that might have some larger impact. So when COVID started, I got 2 separate calls. One was from Amazon and one was from Facebook. But they basically said the same thing. We just sent everyone home, and we don't know what to do. We don't know how to run. Nobody did. There was one single Chinese company that had gone from being an on-site company to fully remote. And there was one single paper analyzing their experience. Other than that, there was nothing. Nobody knew. Very early in lockdown, largely because China was in advance of everyone else, the Chinese search giant Baidu released a paper on their experience with their employees and their engineers in particular in lockdown. And it was fascinating, and I think amazing, particularly for a Chinese company to share this information with the world. Just being really transparent. Here's where we're struggling. Here's where things are working out better. But no one had looked at it. So me being a weirdo, I said, sure, I'll look at this for you 2 giant profit printing organizations for free, philanthropically, as long as it's okay if I tell everybody what I find. And we found a lot of fascinating things just about working remotely, your whole life going through a camera. But it also, if you're a mad scientist, think about what I had. I had the data from one of the largest companies in the world and data from the company that connects over 1 billion people together. I got to see everyone's life, almost in real time. Everyone whose lives were going through cameras. I could track all of it. I told them I wouldn't share anyone's individual data back, but we'd look and see. And 2 things they were particularly interested in. One was how Can they be an inclusive company when everyone's home and remote and going through cameras? And the other is how to be innovative. We're on a university campus. This is the level of sophistication, quite frankly, that most of us put into innovation or collective intelligence, which is, what if we just slam a whole bunch of very smart people together in one place and then cross our fingers? Like, density equals serendipity is about the level of sophistication that goes into a lot of innovation research. But we got to watch everyone's life going through a camera and seeing what made people, not a person, what made people smart. What were the features of collective intelligence? And, we found all sorts of things. Smaller teams were smarter, but they still had to be teams because diverse teams were much smarter than homogeneous teams. In fact, teams that were too similar, they were dumber than the individuals would have been by themselves. Your brain does this funny thing. You hear someone who's so much like you say something, and you almost treat it like it was your own idea. Like you don't check it. You're under-skeptical, even than necessarily you would have been with yourself. So we have diversity, and we have small teams, and then flat hierarchies. So we could literally watch people taking turns in their discussions. We could watch them taking turns on a Google Doc or things like it. We could watch them taking turns in online discussions. The more equitable the turn taking, the smarter the team. Even if one person on the team was a Nobel Prize winner and the other was just an undergraduate intern, one's the senior vice president of such and such and the other is a first year hire, when they were collaborating, it disappeared. And that was one of the key ingredients of brilliance. So we began experimenting with a new AI to maximize collective intelligence of teams. Because we saw these interesting dynamics. Even the smartest teams, you can look, for example, in science, the people who publish groundbreaking research. Over time, that truly brilliant team publishes more and more papers, but they become less and less impactful over time. And this really fascinating thing happens. One new person enters the team, and whoosh, they suddenly get their impact back. And so we started thinking, well, what if we could, especially with all of our lives being remote, it makes it really easy. What if we could build an AI, we call it the matchmaker, that could dynamically take a whole social network and find the smartest teams and remix them over time. So in fact, it's not just a matchmaker because it would break connections as well. Right now, the two of you, you've been talking too much, you're thinking too simply. So we're going to break you apart so your opinions become more independent of one another, which is another concept of diversity. I should note, diversity can cover a lot of ground. So I won't shy away from gender diversity on teams has been well published on, and it improves intelligence, racial diversity, socioeconomic diversity. We can go through a very long list. People who smell more similar tend to strike up friendships. So that's a function of sameness. People with more similar intestinal flora and fauna are more likely to become friends. Who knew that we were all basically a bunch of terrestrial spaceships being piloted by horny protozoa that are just looking to get it on? But to some limited degree, we are all of these things, and all of those dimensions of diversity don't equally matter, but they all play out here. But the other thing we found is that trust also mattered. That if in some sense, if a team was maximally diverse, I mean, first off, maybe they don't even literally speak the same language anymore, but you see trust. And so as we began to look at it, we found that the smartest teams had this fundamental tension. They were pushing the diversity side of their team makeup. Different expertise, different background, different life experiences, different genders, all of it. But there was almost always some shared dimensions. some dimensions of similarity. We called it complementary diversity. So within the smartest groups, there was a lot of differences, but there were core elements that brought people together. And we began looking at what is going on here. So, I mean, here's the funny background for me on all of this. After I started was the founding chief scientist at the AI for Hiring, a company called Guild, and Google was our customer, and Salesforce, and Rolls-Royce, and Nestle. They didn't need us to know who was graduating from Stanford or Cambridge, but they wanted us to find everyone else that they should have hired, but otherwise they'd never find. So that was our job. And it was a great experience, sort of building this system, particularly given, as you hopefully are well aware, AI itself can be really biased also. So how do you build a system that, in a funny way, complements human biases? So our AIs has weaknesses and humans have weaknesses. How do we make certain they don't have the same weakness that just feeds on itself? Instead, we can fit them together. Let me be super clear. This is not like I have a script, as you can clearly tell, but this is even off script from the one that's running in my head. All AI is biased. All humans are biased. All cockroaches are biased. All cognitive systems. There's a fundamental, you may know, time and frequency trade-off in vision and in sound. You can't perfectly know the timing and the frequency of a thing. Position and momentum trade-off fundamentally in quantum mechanics. You cannot precisely know the position and the momentum, the direction and other things of a particle in space. Well, it turns out in machine learning, we have something called the bias variance trade-off. And in any complex system, something that we'd really be interested in solving, where there's no absolutely right answers, there will always be a trade-off there. And so these systems are always biased. What's hopefully wonderful is that doesn't have to be the end of the story. We can be very thoughtful about that bias, and we can still build systems that can improve people's lives, not at the expense of some subgroup, but that can genuinely work across large populations of people and improve things. I will note that job at Amazon, one of the other things they wanted me to do was build an AI to decide who to hire. And I looked at the system they were working on, and I told them it wouldn't work. They built it anyways. And it was very public. It wouldn't hire women. So they built a system, they trained it on their entire hiring history. You might be able to guess what the hiring history of a large West Coast tech company might look like. And so it's not like these things know anything. If you're wondering, GPT isn't intelligent the way we're intelligent. It's not a reasoning thing. It has no agency. If you're worried that you ever hurt its feelings, I wish we had any idea how to build all that stuff. We cannot. What it is the world's largest, most sophisticated autocomplete. And what is interesting about it from a scientific and a technological perspective is how far that gets you. Wow, it is an amazing tool. But the way I often like to describe it is GPT-4, which, by the way, can pass all the U.S. medical licensing board exams in most U.S. states, the bar exam, law exams in most U.S. states. It can pass all of our standardized exams to go to graduate school. It knows everything, and it understands nothing. The understanding is us. And that is, by the way, what I've been giving talks about down in London this week, is we need to get a much better handle on thinking somehow GPT is, one, going to wake up and go Skynet on us. No. Again, this is sort of the thing you shouldn't say in public, but I wish we had a Skynet problem. I wish we had any idea how to build something like that, but we do not. Nobody does. But the wild overpromising of what it can do. I don't think there's ever been a more overhyped and yet underappreciated technology at the same time, because it can do amazing things. The sorts of stories I'm sharing are all AI-driven stories. But you will note the common thread across all of them is that the AI is a tool. and the creativity is human. And maybe that won't hold forever. I don't think that there's something fundamentally special about human brains compared to AI, but for the time being, until we have a major breakthrough, at least in causality, if not something else, that's what we're looking at. An amazing tool. And you're the artist. Ever let the paintbrush do the painting for you, then, well, we already know what you get. You get people with little flipper fingers and weird images. So I'm in this moment of building an AI that can dynamically create the circumstances to maximize collective intelligence. In fact, we've taken all of that and put it into the human trust. And so we're actually going to release it all for free and let companies reap some benefit from it. I kind of suspect that companies having a greater sense of the value of building richly diverse teams of people that not only diverse in an immediate sense, but also that your employees disagree with you, and that's not a bad thing. I want my students to disagree with me. I want my employees to disagree with me. I want them to be right when they do it, but unfortunately, if we already knew they were right, then it wouldn't be science. So I actually only have one interview question, either to join my lab or one of my companies. Pitch me a mad science project. Come up with the thing you wish you could do that would change something fundamental about the world that matters to you. And it doesn't matter if you know how to do it or not. The interview is an hour in which you and I work together to try to come up with an idea that works. And if we came up with a better idea together than I think I could have come up with by myself, then you got the job. And if you don't know how to program, I'll teach you how to program. And if you don't know about brains, I'll teach you about brains. If you don't know about math, that's hard, but I got introduced to advanced math later in my life, so in theory, anybody could. But the one thing I can't teach you is how to have an idea I wouldn't have had. And although I think I can help with this, I can't magically give you the courage to tell it to me when you think it's not what I want to hear. So that's what I'm looking for. In fact, I think that's what everybody should be looking for. And it would be even more amazing if those same people had this magic paintbrush that would give them all the world's knowledge in their pocket, as long as they can supply the resilience and the creativity and the self-assessment and all these other things. Neuroscience of trust. So I'm working on this AI that we're releasing out into the world, and it's a space I've worked in for a long time. Ever since I was the chief scientist of Guild, people have been paying me an unconscionable amount of money, which I could not take, but we put it into the nonprofit work, to get up on a stage and argue the business case for diversity. And let me be clear, it is a super easy case to make. The research is wildly one-sided. Not because people that would disagree with the idea never look at it, but the results are really, really strong, both out in the world and in the lab. Boards with at least one woman on it. I was on an advisory board for a large bank when we did this analysis and released it. Boards with at least one woman on it return 3% more to their shareholders. Boards with 3 or more women return 5% more to their shareholders. Entrepreneurial teams in London that are relatively more diverse are pronouncedly more successful. And then just the core research, as we had done. When people bring different things to the table on a team of people, a community, the community is smarter. So I started giving this talk in 2014, and it's 2024, and I'm still getting invited to give this talk, which is so easy to make. And yet, again and again and again, I get invited to make it. And particularly during lockdown, and I'm doing this talk remotely, and when you give a remote talk, it's just like a blank screen. You can't see anyone. You're just talking to nobody. It's not fun. I like this. I once gave a talk to 30,000 people. I gave the closing keynote at the Grace Hopper Conference, the Women in Technology Conference in Orlando, a place I would not be but for having been invited to give a talk. And it's like giving a talk to the weather. Like you tell a joke and there's a squall of laughter that moves across the room and no one's looking at you. And I couldn't understand because there was the screen, like 2 screens about the size of this behind me, but like even like the front row, no one's looking at you. Someone, I should dig it out, someone sent me a picture from the audience, just like unsolicited. And I realized these weren't the big screens. There was a stadium-sized screen above me. In the picture, you can't see me. You have to like zoom and zoom and zoom. No one was looking at me. But it's amazing. Quite apart from science. In fact, to any of you who are students, university here or younger, I will tell you what my dissertation advisor told me, which is what his dissertation advisor told him. Science is a story. And that story should be about an hour long. The last part I didn't really pick up on too well. If genuinely, particularly if there are any grad students or even undergrads here, if there is an open stage, someone better be beating you off with a stick. Because if you are not on that stage giving a talk, I don't care how many times you've given the talk on your research before, give it again. You know that old adage, you don't really understand something until you taught it for the 6th time? Trust me, you do not understand your research as well as you do. And there is nothing like watching an audience stare back at you and ask you questions that you never thought of to really get into it. Science is a story, and it's more than just that. It's that your one little experiment is just itself a single data point. You need to tell a story that explains it all of the research, even the stuff you disagree with. You don't get to just say, I don't like it. You have to come up with a story that explains why all of this stuff is going on at the same time. And it turns out once you get there, it really is a story. And being able to bring people through a story is an immensely powerful talent. And it's not coincidental that most of the most famous scientists in the world give great talks. And the people that stand up there and read their dissertation to a crowd in a monotone have a much harder time to move on. I could take that, but believe me, I want to stay on this neuroscience of trust thing. So, why is this so hard? Why do I make the same case over and over again, and I'm far from the only one? Well, unlike a lot of people working in this space, I happen to be a neuroscientist. I mean, again, the lazy kind, but still, I know a lot about neuroscience. So I thought, what if there's something about our brains that's making this hard? What if there's a reason why there's this overwhelming evidence and this clear argument, and everyone nods their head, almost everyone, and then we just seem to end up in the same world with the same challenge over and over again. So in the midst of this, I began wondering, how does our brain respond differently when we meet 2 strangers? Say they're interviewing to be your student, and you've given them this insane question to answer, and you're just being kind of weird to them. Well, but one of them looks and smells a lot like you, and the other looks different, and they've got a different accent than you, and everything's different. On paper, they look very similar. Amazing people. They would never have gotten through the door to get to your interview if they hadn't been amazing. But in person, one's very similar and one's very different. Well, let's talk about rats. The classic experiment with rats is rats solving a maze. So you take a rat, you put it at the beginning of a maze, it wanders, and then it finds the cheese. In fact, the classic finding would be if you put it back in front of the same maze, it gets a little bit faster, and then it gets a little bit faster. And pretty soon, it's just beelining right to where the cheese is. And then someone asked themselves, yeah, so they're learning, but explain to me how they know to turn right at the beginning when they only got the cheese at the very end. That may not sound like a deep question, but genuinely, if any of you are engineers, how would you build that? How would you instantiate that in a machine or in a brain? How would you know to associate an award, a distal reward as we might call it, that might happen minutes later with a decision that happens right now? Well, this interesting thing, it's actually really relevant because the way that we solve this is an algorithm called reinforcement learning, which is famous because reinforcement learning developed by Demis down in London beat the world's best Go player. It folds proteins better than a human being can do it. So reinforcement learning is this amazing form of artificial intelligence, machine learning. But we know about reinforcement learning from studying rats, because what we saw was if you put a little wire, or more likely in a modern experiment, it'd be super fine glass filaments, down into a rat, and you look at various areas of the brain, their hippocampus and their frontal lobes and their basal ganglia, where some of their reward centers are. Rewards like dopamine. This reward hormone neurotransmitter that essentially is a reward in the sense that when it gets released, you're going to do that same choice again. It doesn't necessarily make you feel any better. We also, very kindly, we make our own endogenous opioids. If that sounds like opium, then you get the picture. That's the reward in our brain that makes us feel good, but they're different, and that explains some of the craziness that ends up happening with people that get really dysregulated in their reward systems. But we watch this rat, and it's wandering its very first time through a maze. Nothing's going on. There's a lot of frontal activity and prefrontal activity in its brain as it's making choices and it's trying to figure out what's going on. And finally it gets to the cheese, and you see release of dopamine. And all this activity in an area called the nucleus accumbens, and a related circuit that involves the nucleus accumbens and the anterior cingulate cortex, depending on the rat's experience, maybe the amygdala, and prefrontal. Rat doesn't have a prefrontal cortex as expansive as we do, but it's got a little one, and lots of activity. And then you put it back to the beginning, and it starts going through the maze, pretty randomly, because this is still a pretty new maze, but something different happens this time. It doesn't wait until it gets to the cheese. Suddenly, at some point, a couple of turns away from the cheese, the dopamine gets released, even though the cheese isn't there yet. And once that dopamine is released, bzz, 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 the rat goes straight to the cheese. You might think it remembers where it is. And it does, but brains are a little more complex than that. But that's essentially what happened. In some level, this rat's brain has figured out where it is. It knows exactly how to get to the read. And so rather than waiting, it gets the reward right there and then. In fact, it gets a negative reward if there's no cheese when it gets there. But if the cheese is there, that's it. There's no second reward. After a lot of training, you drop the rat in front of a maze that it's recognized, bam, dopamine, just from recognizing the maze, long before it gets the cheese, and it goes straight to the cheese. So we have these two different brain states for a rat, the unfamiliar maze and the familiar maze. And yes, I'm going to really simplify this to tie it into trust, but it works pretty well. With the unfamiliar maze, you see lots of effortful prefrontal activity as it's navigating and remembering and exploring. And with the very familiar maze, you get an immediate reward, and then what we neuroscientists call automaticity, just straight in through the maze, a beeline, very little frontal activity because it's not thinking about it. It already knows how to get to the cheese. This is pretty much what happens when you're meeting those two strangers. Even though they're both strange, so the parallel isn't perfect, it isn't a maze you've seen before, but someone in what in psychology we might call your in-group is a bit like a solved maze. And in fact, someone who is in an out group is like an unsolved. And when you compare them, when you meet that person in the in group, you see an immediate dopamine reward. And when we talk about trust, like collaborating with a stranger, you don't see in that context a whole lot of additional frontal activity necessary to share trust with that person. Does that mean we can't trust people that are different? No, actually, in the other condition, we can build a strong, trusting relationship. But it is effortful. There's no upfront reward. The reward only comes after the trust is paid off. And the trust is earned, much like the rat exploring the maze, through effortful prefrontal activity. Particularly in this case, medial prefrontal. So as we go out here, things tend to be a lot more concrete. And if you go in here, you get more into long-term and emotional spaces. So people can trust one another. So why isn't that the end of the story? Well, because this story is a story of real people in the real world, not in a lab. So the thing is, when you do your job, or you're studying at school, or you're collaborating on an intense project, that also draws on all of those frontal resources. All of that activity you're using to share trust with a stranger, suddenly you're also drawing much of it to be able to do the very thing that the two of you are trying to collaborate on. And what's fascinating is what that does to trust. So let's run an experiment. We're not going to be super tricky. You know, sometimes you might hear of psychology experiments where you do really cruel things. One of my favorite cruel experiments of all time was done by a former professor of mine, a professor of interpersonal relationship. They would bring two newlyweds together and then tell one of them, I think at random, that they needed to give a big public talk. And despite the fact that I'm a weirdo that enjoys winging it, most people, it turns out, really don't like giving public talks. Like, honestly, they'd rather get shocked than give a public talk. So it's a common negative stimulus for psychology experiments. So this person, and then you separate them, but you allow them to send notes. So the one who's going to give the talk can send notes to the other one to ask for help, and the other one can send them back and give concrete instrumental help. They can give emotional support, all the thing. But of course, the experimenters are intercepting their notes and then taking out like the emotional support stuff and just saying, figure it out yourself. I thought you were so smart. Well, turns out when you put people under enough stress like that, something really interesting happens. You then measure when they're back together again how often they touch each other, and if they don't, then they're almost certainly going to be divorced within the next year. Touching rates are a big predictor of relationship stability in newlyweds, it turns out. But you got to put people under pressure before it really becomes diagnostic. So, we're all bastards. And we do cruel, cruel things. Like, let's run an experiment where we're going to have a collective intelligence. Everyone's a stranger, but we're going to get a bunch of very different people to participate in the experiment. And it's actually kind of simple. I won't even go into a lot of detail here. We'll just say to be successful, and actual dollars get paid during this experiment. So you earn money in the experiment. And to earn those dollars, you need to collaborate within this game. And you find one or more people to collaborate with, and depending on how you can share information in that collaboration, you get more or fewer dollars. So before the experiment happens, we have a pre-interview in which we ask the participants to explain, if not the experiment, explain the rules. You understand what you're being asked to do and how you're going to do it. Almost everyone figures it out. I need to go find the people that are the most different to me. Because when we bring our information together, that difference will produce the most dollars. Almost everybody gets it right away, and they are 100% right. And then you start the experiment, and it's a little intense. There's some cognitive stuff, and there's a lot of people, and it's sort of social. And almost immediately, everyone finds the person who's most similar to them and collaborates with them. The exact opposite. What they themselves said was the rules were. And then that isn't even the wildest thing. The wildest thing is that in the post-interview, at the end, they come up with these explanations. Now, I didn't appreciate the way the rules worked. I thought I needed to find someone who's really different, but actually we need to be fast, and fast is just easier with. And they were wrong the second time. They were right the first time, but now they completely changed their perspective, and not because they're lying, and not because they're fools, and not necessarily because they are racist or sexist, although, of course, there can generally be an element of that. But we saw this in everybody. Everybody. To some degree. There's heterogeneity into the amount of which people behave like this. But everybody behaves this way at least a little bit. And the reason is, as soon as there were stakes, as soon as they needed to put effort into regulating their own emotions, to think hard about the problems they were solving, deal with the social cues, suddenly all of the resources that they were initially planning to maybe implicitly deploy to share trust with a stranger suddenly got redeployed to do the task. And now all they had guiding their decision making was that really easy automated system that gave them free rewards for trusting someone who was similar to them. And we were able to look at this in some detail and run further experiments. I don't want that to be the end of the story for the night. It's worth understanding, though. That's what confronts us when we meet people that are different. And again, we're all have heterogeneity here. In this room, some of us are probably much more, as big 5 personality characteristics. One of them is called openness to change. Some of us are much more on the open side. Some of us are much more on the closed side. But all of us are human. We're not villains for being human, but maybe we're a little bit of a villain for not being honest about it and trying to do something. And it turns out there is something you can do. There was, in fact, a wonderful research paper that looked at all of these different ways to change people's biases about one another. The terrible thing was, of the 17 different methods and workshops that they tried, only one worked. So things like implicit bias training didn't change anyone's. There was a great, funny one, if you will, empathy training. They did this in a workplace setting once, and people felt really bad when they continued hiring the same people and not hiring anyone who was new. So what actually changes how people make decisions? Well, it has a very fancy name called counter-stereotypical exemplars. But once you work through that fancy phrase, you realize all it actually means is you need to spend time with people that violate your stereotypes. And it turns out it's a very measurable thing, particularly if you're a neuroscientist, mad scientist, because we can literally see how that circuit changes in your brain when you spend time with people that violate your stereotypes. So it's genuinely possible to retrain our brains. It's not quick and easy. You can't get a pamphlet that tells you how to do it. It's experiential, but it's real and it's possible. And that's part of what we actually look at in the little AI we developed, the matchmaker, is we're looking for that tension between trust and diversity, that complementary diversity. We're looking to bring two people together who are as different as possible and connect them, though, in a way where there's at least that initial kernel of trust that they can start with and continue to build from. And it's kind of fun because, of course, we're working with hard numbers in our system. We can run even game theoretic models to prove it all out. But the net result is a big transformation. And I'll share one truly fun finding from this system. In game theory, there's this famous role strategy called the defector. So a classic is the prisoner's dilemma, where You're being interviewed by the cops, and if both of you stay quiet, nobody goes to prison. But if one of you rats on the other, you go free and they go to prison. And it turns out in a lot of different formulations of this problem that kind of map very loosely onto real life, people rat each other out all the time. And for some people, it is the absolute default strategy, and it's called the defector. What our algorithm found is actually in real-world context, pure defectors are really rare. People don't behave like rational agents, but in a good way. We have a degree of trust, a degree of self-sacrifice, if small, that exists in all of us. In fact, the only famous case that runs counter to that are people diagnosed with psychopathy, which even then doesn't necessarily make them bad people, but it does make it really hard for them to make sacrifices for others because they don't really fully understand why you would do that. So in this algorithm, it quickly would identify who the defectors were. And what I thought it would learn to do was send them off to the cornfields, just like kick them out of the system, or maybe make Battle Planet, like Wrath of Khan style, like send Khan to the terrible planet. I know, this is references that are way older than some of you, but in the original series, they send Khan to this planet where he has to just go fight it out with a bunch of savages. But actually, it discovered the love bomb. It learned that if you took a defector, instead of putting them all together or putting them off by themselves, if you stuck them in the most collaborative subgroups, they changed. It was kind of amazing, right? Like a machine has figured out that even people that routinely backstab each other can change if they get caught in a local community that simply doesn't do it. And that's kind of amazing. Kind of amazing that AI can allow us to learn about ourselves. So I have the suspicion I've gone way longer than was originally scheduled, but I will say two closing things. The first one is I'm happy to hang around and chat and answer questions. If anyone has any about my research, about me, you want to know why the hell I returned to school in 1999 after starting in 1989. 11 years is a little long to be an undergrad, even if it only took 1 year to finally finish. Or just chat about AI. You can probably tell, I've got a lot to say about everything, and the great thing is I'm always right about everything, too. It's a burden, but somehow I've been managed to make my way through life. I don't know what my wife thinks about it, though. But I will say this, even though it's not about AI, and it's not about neuroscience, but maybe it is a little bit about trust. Across my career, I occasionally add these numbers up. I may have shared this on the last talk. I looked how many data points I've analyzed in my career. At Guild, for example, I had a data set of 122 million people and hundreds of thousands of data points, at least in theory, on all of them. For those of you who are data wonks, when you work with real-world data, almost all of it's missing data, and you have to figure out what to do anyways. So we had all of this data to try and figure out who should get hired. But if you add it all up, it's way more than that. I've analyzed, it's approaching 10 trillion data points in my life. If I just tacked on if I just went and collaborated on a project with GPT, I could double that overnight. But for me, all by myself, 10 trillion data points. And here's what's cool. Even if you think of science, technology, engineering, mathematics as this dry space of numbers or machines, my numbers tell me a story. And the story is this. If you want an amazing life, you have to give it to someone else. And that's all I've got to say tonight. So thank you very much. And again, I'm happy to hang around and answer questions.